It's a pleasure to be here, and it's very nice of all of you to show up so early in the morning. So as Ashley said, my talk is on classical verification of quantum computations. And I'm going to start by telling you what it means to classically verify a quantum computation. So the way to think of this question is you have an experimentalist. She's considered the classical being, and she has access to a quantum computer. Her goal is to verify that this quantum computer is behaving correctly in the sense that its behavior is consistent with our theoretical model of what quantum computers should look like. Now, the way she's going to do this is she's going to program the quantum computer to perform a specific quantum circuit. She can choose any quantum circuit. And we'll assume that the output to this quantum circuit is a single classical bit. So it's either 0 or 1. And now the quantum computer is going to report some output. And the goal of the experimentalist is to verify that this output was actually obtained by performing the requested quantum circuit. Now, when you look at this question, the first thing you might think is, well, why can't we use the standard scientific method of predict and test? The problem is that the scientific method falls apart in the context of quantum computations. So I think all of you here are well aware, but the description of an n-qubit quantum state requires exponentially many parameters. And this is because a quantum state is written as a superposition over all bit strings of length n. So its representation, it can be written down as a complex vector in 2 to the n dimensional space. And what this means is that the experimentalists can't even write down the state of the quantum system, let alone predict the outcome of the quantum computation. And it actually gets a little bit worse than this, because not only is the state very hard to write down, but classical access to quantum systems is extremely limited. So this experimentalist can only access the quantum system through measurement. And if she measures this system, she'll obtain a string x with probability alpha x squared. Now, due to Holevo's theorem, we know that a classical measurement of a quantum system can reveal at most n bits of the system. So what I've told you so far is that not only are quantum systems exponentially complex, but they're also exponentially private. And this is what makes the question of testing quantum computers such a difficult question. So now I've told you what it means to classically test quantum computers and why it's so difficult. Now I'm going to motivate it from a few different perspectives, starting from the philosophical perspective. Here the question is whether we can test quantum mechanics in the high complexity regime. So this is an inherently difficult question because as we reach the high complexity regime and we see this exponential scaling, we're no longer able to classically predict the outcome of the system. So if we could classically test quantum computers, this would serve as a method for testing quantum mechanics in the high complexity regime. Now this philosophical motivation links directly to a practical motivation. So as you all know, we're approaching an era in which we expect to have quantum devices with 50 to 100 noisy qubits. At this stage, it's unclear whether useful computations are possible, but what is clear is that we won't be able to classically simulate these computers anymore. And given this, the question is, how can we test these upcoming quantum devices? Now, the final motivation comes from complexity theory. And in complexity theory, one of the most well-studied questions is whether it's easier to test the output of a computation than to actually compute the output. And you can think of this question of classical verification of quantum computations as exactly the question of testing versus computing. Because here I have an experimentalist. She can't compute the output to the quantum computation, but she still wants to be able to test it. Now, in complexity theory, the answer to this question of testing versus computing has been a resounding yes. And to make progress on this question, we looked at a different model of proofs called interactive proofs. And in interactive proofs, the output of a computation can be tested through interaction. So to see it in this model, I would allow the experimentalist to interact with the quantum computer over some number of rounds, and as a result of this interaction, she should be able to verify the output of the quantum computation. Okay, so this question of classical verification of quantum computations through interaction was first stated by Daniel Gottesman in 2004. And here the experimentalist is modeled by a classical computer, and she's referred to as the verifier. And the quantum computer is referred to as the prover. And now the goal of the verifier is to interact with the prover over some number of rounds in order to verify the output to a quantum computation. So this protocol should satisfy two requirements. Oops. The first is that if the prover is honest, the verifier should accept. If the prover responds with anything but the correct outcome of the quantum computation, the verifier should reject. So this is what it means. This is what the protocol would look like. And now, since this question was stated in 2004, it's been extremely well studied, but we studied it in two different models, which were relaxations of this original question. And here are the two models. The first allowed the verifier access to a small quantum computer of his own. And the goal was to use this small quantum computer in order to verify a much larger quantum computation. And this model was studied in two different lines of work since 2008, and it was shown to be possible. So it was shown that the classical verifier could use this tiny quantum computer in order to verify a very large quantum computation. And now in the other line of work, we went back to a purely classical verifier, but at the cost of having two non-communicating provers rather than just one. And in this model, the provers are allowed to share entanglement. And it was shown in a paper by Raikar Ungar Vazirani in 2012 that in this model, we can also verify quantum computations. Now, in this talk, I'm going to go back to the original model with the purely classical verifier and a quantum prover. The reason this question has been so difficult is because there's an extreme power imbalance here. There's an extremely weak verifier who's only capable of classical computations and a much more powerful quantum prover. So the question is, how can this classical verifier gain any leverage over the quantum prover? And I'm going to address this question by taking an upper bound on the power of the quantum prover. So the quantum prover is quite powerful, but he's still just an efficient quantum machine. He's not all powerful. So what that means is I can use an assumption that this quantum computer cannot solve certain problems. So there are certain problems which are too hard for even an efficient quantum computer. In other words, I'm assuming quantum secure cryptography. And what quantum secure cryptography is classical cryptography that a quantum computer cannot break. So the way to think of it is maybe there's a one-way function which the quantum computer cannot invert. And more specifically, I'm going to rely on the assumption of learning with errors. This is currently the leading candidate in quantum secure cryptography. And essentially what this assumption is, it's saying that there's a system of noisy linear equations. And when I assume that learning with errors is quantum secure, I'm assuming that even a quantum computer cannot solve the system of noisy linear equations. Okay, so far what I've done is I've said there's a huge power imbalance, and how I'm going to address it is by upper bounding the power of the quantum prover and saying that there are certain problems that the quantum prover cannot solve. But this isn't fully addressing it, because the verifier is still much weaker than the quantum prover. So the way I'm going to get around that is by giving the verifier some power that the quantum prover does not have. What I'm going to give the verifier is something called a trapdoor. Now, in the one-way function example, the trapdoor would allow the verifier to invert the one-way function. And since the prover doesn't have access to the trapdoor, he still can't invert it. So by giving the verifier access to the trapdoor, I've given the verifier a capability that even the quantum machine does not have. And this is my way of kind of taking care of the imbalance and making sure the verifier does have some leverage over the quantum prover. Okay, so this was a setup. And now what I'm going to tell you in this talk is that classical verification of quantum computations is possible, assuming that the learning with errors problem is quantum secure. And I'm going to proceed in two steps. In the first step, I'm going to tell you about the exact cryptographic primitive that I'll be using. It's called Trapdoor claw-free functions, and it can be built from learning with errors. And I'll show you how this primitive can be used as a test for quantumness, so to test that a machine is actually quantum and not classical. Then I'll go towards the more general goal of showing how this same primitive of trapdoor claw-free functions can be used to classically verify general quantum computations. Okay, so let's start with trapdoor claw-free functions. Now, a trapdoor claw-free function pair is a pair of functions which are injective, and they have the same image. And there's also a trapdoor, which allows for efficient inversion. So there's an algorithm which takes as input a trapdoor and an image y, and it outputs the two pre-images of y. So let's call those x0 and x1. The final condition is called the claw-free condition. And what this says is that without the trapdoor, it is hard to find any pair of overlapping pre-images which map to the same point. And this pair of overlapping pre-images is called a claw, kind of just because of this picture. So this is what it means to be claw-free. And when I'm assuming the existence of trapdoor claw-free functions, what it means is that I'm assuming that both quantum and classical computers cannot find a claw if they don't have access to the trapdoor. Okay, so this is a primitive. Hopefully it's clear to everyone. Now, the reason this primitive is so useful in the quantum setting is because quantum machines have this unique capability where they can sample a random image y and create a uniform superposition over the corresponding claw, so over the two pre-images of y. This is very easy for a quantum machine to do, and in a few slides I'll tell you exactly how it's done. But for now, I'm just going to tell you why the superposition is so interesting. So the first thing you might think when you look at the superposition is that it seems to contain information about both pre-images, but I just told you that even a quantum machine should not be able to sample both pre-images. He shouldn't be able to find them. Now, even though the state seems to contain information about both pre-images, of course, to get any information, the quantum system would have to measure it. So now I'll tell you what happens if the quantum computer measures this state in two different ways. So in the first method, the quantum computer can just measure the superposition in the standard basis. If he measures it in the standard basis, he'll obtain either 0x0 or 1x1 with equal probability. Nothing interesting is happening here. This kind of thing can be reproduced by a classical probability distribution, because at this point, all the quantum computer has done is he sampled a random pre-image image pair. So there is nothing special about that. Now, the reason that this gets interesting is because the quantum computer did not have to measure the state in the standard basis. He could have measured it in the Hadamard basis. And if he measures the state in the Hadamard basis, he'll obtain a string D, which satisfies this equation. So to break this down, I'm thinking of the two pre-images x0 and x1 as binary strings. And then I'm taking the bitwise XOR, and then I'm taking the inner product with D mod 2. So this is where the fact that the quantum machine has the claw in superposition is really coming in handy, because the quantum machine is obtaining a string D, which is correlated with both pre-images x0 and x1, even though he himself can't find both pre-images. He can't hold them at the same time. So this is the part that we don't expect to be reproducible classically, because it's taking advantage of the fact that the quantum machine can have this special superposition. And to formalize this intuition that it shouldn't be possible classically, I can introduce something called an adaptive hardcore bit, which is a strengthening of the claw-free requirement. So remember, the claw-free requirement says that it's hard to hold two pre-images at the same time. The adaptive hardcore bit says not only is it hard to hold both pre-images, it's hard to hold one pre-image and even a single bit of the other pre-image. And the reason this is relevant is because if you think of this string, string D, if the computer knows one pre-image and a string D, that means he knows one pre-image and one bit of the other pre-image. So that's exactly what this adaptive hardcore bit requirement is getting at. Now, in a joint paper with Zvika Berkowski, Paul Cristiano, Umesh Vazirani, and Tomas Vidic, we built a trapdoor claw-free function from learning with errors. What this means is we said that the trapdoor claw-free function is secure. It's hard to find a claw as long as a learning with errors problem is not breakable by a quantum computer. And moreover, we showed that not only is it claw-free, but we showed that this adaptive hardcore bit requirement holds. So this implementation can be used to kind of get this quantum advantage. And that's what I'm going to show you next. I'm going to show you how this implementation, or how this specific trapdoor claw-free function, can be used as a test for quantumness. So it can be used by basically using this task to verify that a machine is actually quantum. Now, before I do that, I have one gap to fill in. So remember, I told you that it's very easy to create the superposition, but I didn't tell you how. So let's just go through that now. What the quantum machine does is he first creates a uniform superposition over the domain. That's easy, just he applies the Hadamard transform. Then he applies the classical function in superposition. So he appends an extra register to his state, and he either applies F0 or F1, depending on the first bit B. Then he measures that last register to obtain an image Y. And here's where the 2-to-1 property comes up. Because if the function was not 2-to-1, let's just say it was injective, then the state would collapse. But since it's 2-to-1, the state collapses to exactly the 2 pre-images, which are consistent with the image Y. And this is due to the entanglement in the state. So as a direct result of measuring this image Y, the state collapses to the initial state. And this is all. So it's a very easy thing for the quantum computer to create this superposition over a claw, given only public access to the function. All he has to do is be able to evaluate the function. OK, now I told you how to do this, so let's go into the test for quantumness. What does it mean to test that a machine is quantum? So this is a protocol between a classical verifier and some machine, and we don't know what this machine is, but this machine is claiming to be quantum, and we'd like to test it. Now, this protocol should have one guarantee. If the machine passes, either it's a classical machine, which is taking an exponentially long time, or it's a quantum machine. That's it. OK, so this type of protocol, which satisfies this guarantee, could be used as a protocol for verifiable quantum supremacy. So it's for quantum supremacy because it's easy for quantum machines, hard for classical, and I'll show that it's actually verifiable classically that a quantum machine is passing this test. OK, so now let's build this protocol from trapdoor claw-free functions. So here's how it goes. The verifier selects a trapdoor claw-free function pair F0, F1. He hands it over to the prover. So this is kind of, he hands over a description of the function so that the prover can publicly evaluate the function. The verifier hangs on to the trapdoor and doesn't show it to anyone. Now, if the prover was actually a quantum machine, he's supposed to create a superposition over a random claw and report the image Y. If he's not a quantum machine, we have no idea what he's doing, but all he has to do is report an image Y to the verifier. Now the verifier chooses to test the prover in one of 2 ways. Either he asks for a pre-image, or he asks for a string D, which satisfies this equation that we talked about earlier. Now, if the machine was a quantum machine and he did create this superposition over the state, then this is very easy. If the verifier asks for a pre-image, the quantum computer measures it in the standard basis. And then he gets either 0x0 or 1x1. If the verifier asked for a string D, then the prover measures it in the Hadamard basis. And now he'll obtain a string D, which satisfies this equation. Now, the last step is that using the trapdoor, the verifier can extract x0 and x1, the 2 pre-images of Y, and he can check that the prover is actually passing the test. So he can look at this string D and check that it satisfies this linear equation with respect to the 2 pre-images of Y. So far what I've done is I've told you that this protocol is verifiable and it's very easy for a quantum machine. But I wanted it for verifiable quantum supremacy, so I want to say that it's very hard for a classical machine to pass this test. Now, what would happen if a classical machine could pass this test? So let's say the classical machine could pass the challenge whether the verifier asked for a pre-image or a Hadamard basis, or a string D. Then what we could do is we could rewind the prover. So we could run him on the pre-image test, extract a pre-image from him, rewind him, run him on the D or the Hadamard test, and extract a string D for him. And by this rewinding process, we can construct a classical machine which holds both a pre-image and a string D, which means he holds both one pre-image and a single bit of the other pre-image, This is violating that adaptive hardcore bit requirement, which was a strengthening of the claw-free requirement. And so this is the reason that it's so hard for classical machines to pass, because we can rewind classical machines. So the first thing that comes up is, why can't we do the same exact thing with quantum machines? And that's because, let's say we ran the quantum machine on the pre-image test. Now he's taking his superposition and he's collapsing it. He's measuring it in the standard basis. I can't rewind him and run him on the Hadamard test. So he can only do one at a time, and that's what gives him this massive advantage. So this protocol actually tests that a machine is quantum. Okay, so now let's look at this protocol and look at all the implications that it gives us. The first is what I just told you. If a machine can perform both tasks, it cannot be classical, giving us a protocol for verifiable quantum supremacy. Now, the next task is pretty interesting. So quantum machines inherently generate randomness through measurements. And one huge cryptographic task is whether we can generate certifiable randomness from quantum machines. So can you run a protocol with a quantum machine where you can certify that it's actually generating randomness? And this protocol also gives a certifiable randomness protocol. And that's because if a machine passes this test, so if he can perform both tasks, but he's deterministic, then I have the same rewinding argument. I can say he holds both a pre-image and a string D, and he's violating the adaptive hardcore bit requirement. So that gives a protocol for certifiable randomness generation. Now, the final implication is, it's not directly from this protocol, but I've also used this trapdoor claw-free structure with respect to quantum computers to build something called quantum homomorphic encryption. And this is a task where a classical client wants to delegate a computation to a quantum computer on the cloud in such a way that the quantum computer can perform on the encrypted data without learning anything about it. So I'll talk about this tomorrow, but this result relies heavily on trapdoor claw-free functions. Now, in this talk, I'm going to go back and show you how these trapdoor claw-free functions can be used for the question of classical verification of quantum computations. Now, so far what I've done is I've used cryptography to create a task which separates quantum machines from classical machines. Now I'm going to use a very similar task to force classical commitments to quantum states. So the first thing I'm going to do is tell you what it means to classically commit to quantum states. And then I'll tell you why this primitive is strong enough to directly give classical verification of quantum computations. So what does it mean to classically commit? Here's what an ideal classical commitment to a quantum state would look like. The prover selects a single qubit state of his choice. He commits to it using a trapdoor claw-free function by sending a classical string to the verifier. Then the verifier selects a measurement basis, either Hadamard or standard. And the prover is supposed to measure his committed state psi in the chosen basis. So what does this protocol mean? What it's saying is that once the prover commits to his state, he has no power to change the state. Even once he learns the verifier's basis choice, he cannot change his committed state. So the purpose of this commitment protocol is to enforce non-adaptivity on the part of the prover. And more specifically, what I'll show is that as long as the prover cannot break the trapdoor claw-free function, his hands are cryptographically tied to the state that he committed to. So he has no power to change it. Now, this protocol was a simplified version for a 1-qubit state. And more generally, I will require classical commitment to n-qubit quantum states. And this protocol is almost identical to the one that I just showed you, but there are a couple differences. So the first is that the commitment string y is a concatenation of n commitment strings. Because there are n qubits, the prover commits to each qubit separately. The second is that the verifier chooses a measurement basis, either Hadamard or standard, for each qubit separately. So now his basis choice is an n-bit string. And now the reason this protocol is so interesting is because here I have a classical string which serves as a commitment to an exponentially complex quantum state. So this is an n-qubit quantum state. It requires 2 to the n parameters to classically describe. Yet all the prover is doing is he's sending a classical string to the verifier. And through this classical string, he's committed to 2 to the n different measurements of this single quantum state. So that's why this protocol is so powerful. And it turns out that it's actually powerful enough to classically verify quantum computations. So remember, our goal is to verify the output of a quantum computation. So now what I'll tell you is how this commitment protocol directly links to verifiability. And then for the rest of the talk, I'll show you how to construct the commitment protocol and how to prove security. So this is called soundness, and what I'll show there is why this commitment protocol actually ties the hands of the quantum prover. Okay, so for this first step, to link commitment to verifiability, let me first just try to give you a very high-level picture, and then I'll fill in all the details. So here's the reason. A quantum state serves as a certificate to the solution to a quantum computation. And the certificate is verified just by measuring it. So this is the rough idea. Measurements of a quantum state serve as a certificate. What this protocol is providing is measurements of a quantum state to the verifier. So now let's fill in the details. To fill in the details, I'm going to go back to classical complexity theory for a second. Now, if you wanted to verify an efficient classical computation, the way you would do it is the way the verifier would do it is by first considering this computation as a 3-sat formula, because you can always reduce to a 3-sat formula. Then he would ask the prover for a satisfying assignment to this formula, and then all he has to do is verify that it's satisfied. There's a direct analogy in the quantum world, and here the 3-sat problem corresponds to the local Hamiltonian problem. An n-bit variable assignment corresponds to an n-qubit quantum state. And the number of unsatisfied clauses corresponds to the energy of the quantum state with respect to the Hamiltonian. So if we take this analogy, I can give you a protocol which a quantum verifier can use to verify a quantum computation. Here's how it goes. So just like the classical verifier considered a 3-sat instance, the quantum verifier will consider a local Hamiltonian instance, and his goal is to verify that the local Hamiltonian has low energy. So what he does is he asks the prover for a ground state, and he verifies that the Hamiltonian has low energy with respect to the ground state. This is equivalent to verifying that an assignment is satisfied. So this is it. It's a simple protocol with a quantum verifier. And the nice thing is that all the quantum verifier has to do to verify is perform Hadamard and standard basis measurements. That's it. So all he has to do is receive the quantum state and be able to perform these measurements, and he can verify a quantum computation. So in some sense, his quantum capabilities are limited. And that's what I'm taking advantage of. So I'm saying that if I want to get rid of this quantum verifier and turn him into a classical verifier, all the classical verifier has to be able to do is force the quantum prover to perform the measurements that the verifier would have. So what the prover has to do is perform these measurements non-adaptively. He has to fix a quantum state and then perform the same measurements that the verifier would have. That's where the power of the protocol comes in, because if the prover was able to change the quantum state, then it's not equivalent to what the quantum verifier was doing. And this is exactly what the measurement protocol is doing. The measurement protocol is forcing the prover to pick a quantum state at the start of the protocol before he knows the measurement basis choice of the verifier. And then it's tying his hands to that state so that once he knows how he's supposed to measure it, he has no option but to measure the originally committed state. So this is the link between the commitment protocol and classical verification of quantum computations. And I'm not going to say anything more about this, so now you know it's enough to verify quantum computations. And for the rest of this talk, I'm just going to show you how to build this commitment protocol and how to prove that it serves as a commitment. Okay, so now we can get into the commitment protocol construction. So here's a reminder of the commitment protocol. I'm going back to the single qubit case for simplicity. So the prover commits to a single qubit quantum state with a classical string using a trapdoor claw-free function. Then the verifier chooses a measurement basis, either Hadamard or standard, and the prover should be forced to measure the committed state in the desired basis as long as he cannot break the trapdoor claw-free function. Now, as the first step, I'm going to show you how the prover actually commits to a quantum state using a trapdoor claw-free function. So let's say he has this single qubit quantum state in mind. And to commit to it, he entangles the state with a claw in almost the same exact way as he created the superposition over a claw in the test for quantumness. So what he does is he samples a random image y, and he entangles the state with the corresponding claw, the two pre-images. And how does he do this? He takes a single qubit state, he appends it with a uniform superposition over the domain, and then he applies the trapdoor claw-free function in superposition. So he either applies F0 or F1, depending on the first qubit B. Then he measures that last register to obtain an image y, and as a result of the measurement, the state collapses so that the only remaining x are the two pre-images of y. So once he measures y, he's done entangling the state with a claw. This is the same thing as what he did to create a superposition over a claw. Now, the classical commitment to the quantum state is the image y that he sampled as part of this process. So to put everything together, here's the commitment protocol. There's the classical verifier, the quantum prover. The classical verifier sends over a trapdoor claw-free function pair to the prover. The prover commits to a single qubit quantum state of his choice by entangling his state with a claw and reporting the image y back to the verifier. And now, remember, the next step is that the verifier is going to ask the prover to measure his state in either the standard or Hadamard basis, and the prover should not be able to change his state prior to measurement. So why does this type of commitment, intuitively, why should it satisfy this guarantee? Now, here's the intuition. So the prover started out with this single qubit quantum state, and he expanded it into a much larger quantum state. So what if we could say something very strong? Like, what if at this point, the prover didn't even have access to that second register anymore? Then, because this is a large entangled state and he doesn't have access to a big chunk of it, he pretty much has no power to change the state. Now, what happens is that this is almost the case because the prover does not know the two pre-images. He doesn't know x0 and x1. So it's almost like he has no access to the second register. So this is the intuition behind why this commitment protocol ties the hands of the quantum prover. And to finish this talk, I'm going to try to fill in this intuition and tell you how I actually prove it. But for right now, I'm going to tell you how measurements are performed. So what I've said so far is that this entanglement with the claw prevents the quantum prover from performing any operations on his state, because he's taken his single qubit quantum state and he's entangled it in a way that he doesn't know what the state looks like anymore. But that statement is too strong, because what I want him to be able to do is not change the state if he feels like it, but only change the state if the verifier wants him to perform a measurement. So if the verifier asks him to perform a Hadamard or standard basis measurement, he should be able to. And that's what I'm going to show you now. So what happens is that the prover has some knowledge, he has the quantum state, but the verifier has some other knowledge. So the verifier knows the two pre-images x0 and x1. He can extract them from y using the trapdoor. So he knows something about the prover's quantum state that the prover himself does not know. And because of this knowledge, the verifier can help the prover perform quantum operations. So if the prover wants to do it by himself, he has no chance. But if the verifier wants him to do it, the verifier can collaborate with him in order to complete this operation. So normally, I wouldn't go into this part because it's technical, but since this is a quantum audience, I'm hoping this will work out. So I'll show you how he performs the Hadamard basis measurements and standard basis measurements. And then I'll go back and I'll tell you more about this intuition for why it's secure. Okay, so let's go into the Hadamard basis measurement. The goal of the honest prover is to apply H to his single qubit quantum state and report the measurement result to the verifier, because that's what the verifier is looking for. Now, the problem is that once the prover commits to his state, he doesn't have this nice single qubit quantum state anymore. He has this much larger entangled state, and he doesn't know how he entangled the state. He doesn't know x0 and x1. And so all of you probably see that because of this entanglement, we can no longer just perform the Hadamard transform on the first qubit. The entanglement is messing that up. So it turns out that, so you can think of this state as some kind of encoding of the single qubit quantum state. And what happens is that the prover can take this encoding and convert it into a different encoding, which makes it possible for him to kind of apply the Hadamard transform with the help of the verifier. So here's what he can do. He can take this state, and he can create this single qubit state. So he's going to measure part of this state, and as a result, it will result in the single qubit state that we wanted up to this Pauli bit flip operator. So just a reminder, the Pauli X operator is a bit flip. It maps 0 to 1 and 1 to 0. And the reason that this is still an encoding, so he hasn't broken this claw-free encryption, is because the prover can perform this mapping, but in a way where R is essentially uniformly random to the prover. So he has no idea what R looks like. But the really nice thing here is that now the quantum prover can just measure that state, and he can hand back the measurement result to the verifier. And all the verifier has to do is XOR the result with R. And the verifier can compute R using the trapdoor, because R will be a function of x0 and x1. So in this way, the prover and verifier can collaborate in order to get this Hadamard measurement done. Now let me fill in the details here, and let me tell you exactly how this is done with the claw-free encryption. So the first thing the prover does is to convert this encryption into the other one. He applies a Hadamard transform to this entire committed state. Then he measures the second register, the register containing the pre-images x0 and x1, to obtain a string D. As a result of the measurement, this is what his state looks like. So now he has the first qubit with the Hadamard transform applied to it, and there's this bit flip operator, which I previously represented as x to the power r. So what R is equal to is the inner product of D with the XOR of the clause. And this is why I said that R is computationally random to the prover, because the prover doesn't know x0 and x1. So this inner product looks random to him. He doesn't know anything about this state. And now what the prover does is he measures the state, hands it to the verifier. The verifier takes that single bit measurement result, and he also asks the prover for the string D from the first step. And he XORs the measurement result with D.x0 plus x1. Okay, so to put all of this together, this is what the protocol is. The prover starts with this large committed state. He performs a Hadamard transform on the entire state. He obtains two measurement results, the bit B prime for measuring the first qubit in the Hadamard basis, and the string D for measuring the rest of the state in the Hadamard basis. The verifier takes as input both of these measurement results. He computes B prime and the XOR with this string D. And that's the final output of the Hadamard measurement. So in this way, the verifier has used his knowledge of the trapdoor and the two pre-images in order to help the prover perform the Hadamard transform on this committed state. Okay, so that's the Hadamard transform. Now, there's also the standard basis measurement. So remember, the verifier is going to ask for one of two basis measurement. The first thing you might think is, well, the Hadamard basis was a problem because of this entanglement. But the standard basis is not a problem. He could just measure that state and he'll get the right distribution. He'll get 0 with probability alpha 0 squared, 1 with probability alpha 1 squared. Now, this is actually a pretty subtle issue. And what happens is, remember the goal of this commitment protocol is to enforce non-adaptivity on the part of the prover. I do not want the prover to be able to change his quantum state based on the measurement choice of the verifier. So for this protocol, what I require to satisfy this non-adaptivity guarantee is that the prover doesn't learn the basis choice of the verifier. And just to be clear, this is specifically for the protocol, and it might not be true for other commitment protocols, but for my protocol specifically, I need the prover to not know the verifier's measurement basis choice in order to guarantee that the prover behaves non-adaptively. So I'm not going to get into that because it's a subtle issue and I don't have time, but I'll ask you to take it on faith that I do require that the prover doesn't learn the basis. And given this requirement, now I need to do something a little bit strange. I need to convince the prover to give me a standard basis measurement without him knowing that he's giving me a standard basis measurement. So essentially, like if you look at this protocol, the prover's perspective is he receives these trapdoor claw-free functions and he's asked for a Hadamard basis measurement. But now what I need to do is keep his perspective exactly the same, but collect a standard basis measurement from him instead. So the only leverage I have here is I can't really do anything about the Hadamard measurement. That's what I'm asking him for. But what I'm going to do is I'm going to change the functions f0, f1, so that as a result of sending him different functions, which are computationally indistinguishable to him, he's tricked into giving me a standard basis measurement even though he doesn't know it. Okay, so this is another nice use of cryptography. And here's how it goes. The functions f0 and f1 were trapdoor claw-free functions. So they were injective and they had exactly the same image. I'm going to instead use functions g0 and g1, which are now injective, but they have disjoint images. So their images do not overlap at all. And now, and the functions f0, f1, and g0, g1 are computationally indistinguishable to the prover. So he can't tell. And now the point is, if the prover commits with g0, g1 rather than f0, f1, this acts as standard basis measurement. So to see this, remember the commitment procedure. He took his state, appended it with a uniform superposition over the domain, and then applied the function in superposition. And now remember when that final register was f0, f1, then when it was measured, because each image had two pre-images, the superposition over B did not collapse. It was preserved, but now it was entangled with something. But now, since the images of G0 and G1 are disjoint, when that last register is measured, the superposition over B will collapse. So measuring this, the image of G acts as standard basis measurement of the state. So that's the point of switching the functions. The fact that the images are disjoint means that committing to the state is a standard basis measurement of the state. And now the nice thing is that the verifier can just look at the image Y and extract the standard basis measurement from it. Because the verifier has the trapdoor, so he can check if Y is an image of G0 or an image of G1. If it's an image of G0, then he stores 0 as a standard basis measurement. If it's an image of G1, then he stores 1 as a standard basis measurement. Okay, so just to put this together, this is a protocol for standard basis measurement. It's almost exactly the same as Hadamard basis measurement, but the first functions are swapped out from f0, f1 to g0, g1. So the verifier sends over g0, g1, asks the prover to commit. From the commitment, the verifier can extract the standard basis measurement. Then the verifier asks him for Hadamard basis measurement just to make sure he doesn't know what's going on, but he ignores whatever the prover sends after, because it doesn't matter to him. So here's the full commitment protocol. The verifier selects a basis choice, either Hadamard or standard. He sends claw-free functions for the Hadamard basis and injective functions for the standard basis. Then the prover commits to the state using the functions that were sent to him, and he sends the classical commitment Y back to the verifier. To obtain the measurement results, and then the verifier asks the prover for Hadamard measurements. And now to obtain the measurement results, if it was a standard basis, all the verifier has to do is look at Y, use the trapdoor to extract the measurement. If it was a Hadamard basis measurement, he uses the Hadamard measurement results and decodes them using his knowledge of the pre-images. Okay, so this is the full commitment protocol. And now I can tell you about soundness. So I can tell you why it is the case that once the prover commits to the quantum state, he has no power to actually change his state. Okay, so in all of these protocols with a quantum prover, the difficulty is that the quantum prover has an exponentially large Hilbert space. So he has this huge space and we have no idea what he's doing, but in order to prove soundness, in order to prove that he's actually performing quantum computation, we have to characterize his space somehow. And for those of you who were in Tomas' tutorial yesterday, he referred to this question as where are the qubits? And he kind of went through all of the different protocols and showed how they characterize the space of the quantum prover. And I'm going to remind you of that briefly now by looking at two of the previous protocols. One where the verifier had a small quantum prover, and the other where the verifier could interact with two quantum provers. And the key step in all of these protocols and in mine is enforcing some structure in the prover state. So saying that through the protocol, if the prover passes some tests or is accepted by the verifier, then we can say something about what his quantum state looks like. Okay, so how is the state characterized in the model with a small quantum computer? Here, the verifier used a small quantum computer to pick some secret error correcting code and encode some qubits. Then he sent them over to the prover. And now, once he did that, he knew that in some corner of the prover's exponentially large space, there were these qubits which were encoded with this error correcting code. He knew exactly what they looked like because he chose the code. And from this characterization, he could then verify the full quantum computation. So here, the characterization is a bit easier because the verifier can actually create the qubits. Now, in the next model, the characterization was a bit trickier because now we have a classical verifier, and he's interacting with two quantum provers. And here, what happened is that the verifier played the CHSH game with the two provers and checked for a Bell inequality violation. And then they showed that if the provers passed with a certain probability, then the provers had to be sharing Bell pairs. So they had to share these maximally entangled states. And then they could use this characterization to force the provers to carry out a quantum computation. Now, in my commitment protocol, it's a different setup. And the first thing to note here is I've dropped the functions G0, G1 because the soundness actually comes down to the Hadamard case with the functions F0 and F1. So I'm just going to focus on that. And here, so when I referred to this protocol, I kept saying that the prover is committing to a quantum state, and this is what his quantum state looks like. But of course, with a general prover, I have no idea what he's doing. I don't know that he is committing to a quantum state. I don't know how he's producing the string Y. I don't even know that he holds qubits. So that's the real difficulty. That's the first step in my protocol. I first need to say something. I need to say that he even holds a committed state. And of course, I can't use previous techniques here because the verifier doesn't have a small quantum computer and the verifier is only interacting with a single prover. So what I'm going to do is I'm going to modify my commitment protocol solely for the purpose of enforcing structure in the quantum state. And here's what happens. The verifier gets this image Y, which is the commitment, and sometimes at random, he's going to ask the prover to report a pre-image of Y. So this is what it looks like. This is a test. And now, if the prover was honest, if he actually held a quantum state and he committed to it, this is really easy. All he has to do is measure that committed state in the standard basis, and he'll obtain a pre-image. And then he passes the test, and everything's fine. But what I want to say is that this test defines a committed state of even an arbitrary prover. So this prover, I don't know anything about him, but all I know is that he passes the test. So when I ask him for a test, he hands back a pre-image of Y. Now, it turns out that just this test can help me define this committed state. So what I can say is that at some point in time, the prover state has this form. So most of this state is irrelevant. Alpha 0 and alpha 1 can be anything. Psi 0 and psi 1 just represent the rest of the prover space. They can also be anything. The only thing I'm trying to get across in this state is that there is a superposition over the two pre-images x0 and x1. And now this seems like a strong statement, and the reason I can say this is because if the prover is passing his test, in order to produce the output for the test, he has to be measuring some part of his space. And when he measures that part of his space, he is obtaining a pre-image because he's passing my test. So all I'm doing is I'm writing down that part of his space and saying, well, it has to be a superposition over pre-images because that's all he can give me that I'll accept. So introducing this simple test round is enough to define a committed state. Because now that I have this superposition over pre-images, I can say this is the committed state, then I can work off of here. So that was the goal of the test round. I actually added this test round to the commitment protocol in order to be able to define a committed state. Okay, so now this is the harder part. So this is a committed state. But the next step is the verifier is going to ask for either a Hadamard or standard basis measurement. And I have to be able to show that when the verifier is asked, when the prover is asked for the Hadamard basis measurement, he does measure this committed state in the Hadamard basis. So what an arbitrary prover could do is, I'm going to assume he's starting with this committed state due to the test round argument. And then he can apply an arbitrary operation of his choice. Since he's quantum, we can call it a unitary operator. And then he can perform the Hadamard basis measurement. The reason this is the most general is because quantum operations are reversible. So I can always assume he does whatever he wants, and then he does the right thing, which is the Hadamard basis measurement. And followed by this, the verifier receives the Hadamard measurement result and decodes it by using the secret decoding having to do with the claw. Now, the point is, his deviation operator U is essentially blind. This was the intuition I gave earlier. So the unitary U is acting on this state, but the unitary U is chosen by the prover, so it cannot be dependent on x0 and x1. Moreover, it's followed by the verifier's decoding, which is also dependent on x0, x1. So the unitary U is essentially computationally randomized by both the initial state and the verifier's decoding. And for those who know, I'm going to use something like the Pauli twirl, which is a technique in delegated computation. But the Pauli twirl is kind of a computational version. And what I show is that this computational randomness limits the prover so much that his unitary U essentially commutes with standard basis measurement. So by randomizing it, I can simplify the unitary U so it commutes with standard basis measurement. And what that means is that the unitary U could have just been applied to this committed state, and then the prover could have performed the measurements honestly. So instead of cheating, he could have just created a different committed state, then performed the measurements honestly, and that's all I wanted to show. All I wanted to show was that there exists a committed state for which, when he's asked for measurements, he performs the measurements. And so this part is this is where most of the proof comes in, because in all previous papers, these techniques were information theoretic because the verifier would perform the encoding. But here, I really need to use this computational randomness, the fact that it's computationally difficult for the prover to find x0 and x1 in order to say that this unitary U is ineffective. Okay, so to wrap up, I focused on the question of whether quantum computations can be verified classically. And to do this, I built something called a classical commitment to a quantum state. And the ideal functionality of this protocol is as follows. The prover should construct a quantum state of his choice. The verifier chooses a measurement basis for each qubit, either Hadamard or standard. And the protocol should force the prover to report the measurement results of the committed state in the basis chosen by the verifier. So the protocol is enforcing non-adaptivity on the part of the prover. He's tied to a quantum state from the beginning, and he can't change his mind. The way this goes is that the prover first commits to his quantum state using trapdoor claw-free functions. And then the claw-free property can be used to force the prover to measure the committed state in the desired basis. And to put everything together, what I've shown is that verifiable delegation of quantum computations is possible, assuming that quantum computers cannot break the learning with errors problem. Okay, that's all. Thank you.
Great. Okay. Thank you very much for that fantastic talk, Camilla. So we have plenty of time for questions. So maybe John?
Well, I have a lot of questions.
Maybe wait a sec for the microphone.
Hold on, please. The mic is coming. In a lot of these protocols, even the simplest ones, where the verifier just gets one bit back, I would imagine that the prover can cheat by, half the time being successful just by total randomness. So there must be some sort of amplification procedure, and I was expecting to see all sorts of arbitrary constants of 2/3 and things. Are those hidden somewhere and just not in the talk?
No, yeah, I just didn't include them in the talk, but yes, the soundness parameter is 1/2 or something like that, which means that if the prover is cheating, then the verifier accepts with probability at most 1/2. And then you amplify to cut that down.
Okay.
Yeah.
Okay, so maybe just in front.
So in the soundness proof, you introduced these test rounds, you said, so that you could force the state to have some structure. So if you don't introduce the test round, I mean, the intuition you had earlier in the talk seemed to suggest that it could still work. Do you know an attack if you don't introduce the test round, or you just don't know?
Well, there's kind of an attack, but it's not concrete. If you don't introduce the test round, there's no reason he has to have pre-images, because you're never asking him for it.
But, I mean, you don't know of a specific approach that you could use to cheat the protocol then?
Yeah. I don't know a specific thing. It's possible that you could use the fact that the Hamiltonian has both standard basis and Hadamard basis measurements to say that the standard basis is telling you something about the pre-images. So maybe. But using the test round made the analysis much easier for me. Yeah.
Okay, further questions? In the back, or the side, sorry.
So at the end, you had this computational limitation where you said that its unitary is somehow random because of the choice of the claw-free function and these things. But I didn't get so the randomness of this unitary, this effective randomness of unitary, why does it help? Like, because you would see if the prover tries to cheat, or what would happen if something would go wrong?
Okay, so the reason these arguments are usually used is because when you have an arbitrary prover, he can deviate in any way. He can choose any unitary operator. But usually you can prove soundness if you prove that the unitary U is restricted. For example, if I was able to say that the unitary U is just a Pauli operator, usually it's much easier to prove security, because you can say, well, a Pauli operator is caught by these types of tests, therefore he's not cheating. So that's the point of the randomness, to take a general unitary U and cut it down to the point that it can be handled by these tests, the test round. And the way I cut it down is I say, it's not general, it's a unitary which commutes with standard basis measurement.
But it means that there is a separate test round for checking this unitary deviation as well.
No, because, so the protocol is kind of split up. There's a commitment protocol, and all I need in the commitment protocol is to guarantee the existence of a quantum state. And then there's this kind of a QMA verification protocol. So essentially what happens is cutting down the unitary U is enough to satisfy the commitment protocol guarantee. Meaning, when I cut down the unitary U, I can argue that there exists a quantum state which he committed to and is measuring consistently. Once I say that, then the further tests are done in the QMA round. So as soon as you have a consistent quantum state, then the QMA testing can be used to ensure that it is a specific quantum state.
Okay, thanks.
Yeah.
Yeah, sure, just now.
So one of the points I appreciated was your verification protocol was a binary decision, right? So yes or no, where yes meant it was a quantum computer and no meant that it wasn't. And I understood the no category included classical computers, but I wasn't sure what else it included. So for example, is a non-universal quantum computer fall into that category, or a noisy quantum device?
Okay, so you're talking about the test for quantumness, not the verification, right?
That's right, yeah.
Okay, so sure, in that, all I'm testing is that the computer is quantum and not classical, in the sense that if it was classical, it would be violating some hardcore bit requirement. So like you said, the limited quantum computer, if all that quantum computer could do is just this test, which is not universal, then it could pass. And noisy quantum computers, that's something that we're working on. We're trying to see if this protocol can be made robust. Yeah.
Okay, so if there aren't any further questions, I have a question actually. So how important is the use of learning with errors in your protocols? Like, is there hope for replacing it with some other crypto system? Let's say learning with errors turns out to be quantumly, crackable. Can we replace it with something else? I mean,
Okay, so we relied heavily on learning with errors properties to prove this adaptive hardcore bit, which is a pretty strong property. Mm-hmm. But that said, I don't know if cryptographers have looked into this, and I don't know that much cryptography, so it's possible that if they looked into it, there are other cryptographic problems which have these nice properties. But I don't know them, that's all. Yeah.
Okay, excellent. Great, well, thank you very much. So I think before we go, oh, we've got one here. Sorry, please.
I was wondering if you talk more about how difficult it is for the prover to distinguish between when the function is two-way versus one-way, like between f and g.
Yeah, that exactly reduces to learning with errors. So
Okay.
all of the computational assumptions I'm using, they all boil down to saying, like, if the prover could distinguish between these functions, then he can break learning with errors. Or if he could break this adaptive hardcore bit requirement, then he could break learning with errors.
Okay, thank you.
Yeah.
Okay, thank you. So before we go to the coffee break, I think that Felix has one or two things to say. But before that, let's thank Amelia again for her talk.